All right, let's talk about AI. We're going to peek behind the curtain today and look at the real engine that makes it all go. And you might be surprised to hear it's not some kind of magic, it's not science fiction, it's calculus. Seriously. And I promise by the end of this, you'll see how this math, which is centuries old, is the secret architect of the AI world we live in right now. So let's just start with the biggest puzzle of all. You've got an AI, and it's learning, right? It's making millions, maybe billions of tiny little adjustments to its internal wiring, trying to get closer and closer to the right answer. But how does it know which way to go? How does it navigate that massive maze from being totally wrong to being unbelievably accurate? To really wrap our heads around this, let's use a simple analogy. Just picture an old school analog radio. You're twisting that dial, trying to lock onto your favorite station, but mostly you're just getting a wall of static. Well, that process, that hunt for the clear music, that is exactly what an AI is trying to do. Now, in this radio analogy, a few different fields of math get to play a part. So linear algebra, with all its vectors and matrices, you can think of that as the raw data. It's the electrical signal that has the potential to be music. And then you've got statistics. Statistics is what lets us measure the noise, the static. That's our AI's error, basically how far off it is from that perfect signal. And that brings us to calculus. Calculus isn't the signal. It's not the static. It's the physical act of turning the knob. It's the tool that gives the AI this feeling, this intuition. It tells it, hey, if you turn this little knob just a hair to the right, the static gets a little bit quieter. It's the active searching process of finding that music in all the noise. Okay, so the radio analogy is great, but let's switch to an even more powerful one. Forget the radio for a second. Let's picture the AI's entire learning process as a physical journey, a trek through this vast and kind of dangerous mountainous landscape. We call this landscape a cost function. Every single point on this terrain, every spot you could possibly stand, represents one possible setup for the AI's internal knobs. Now, the higher up you are on the mountain, the bigger the AI's error. So what's the goal? Simple. Get to the very bottom. Find the lowest valley where the error is basically zero. That valley, that's the right answer. But here's the twist. The entire mountain is covered in this super thick fog. The AI is totally blind. It has no map. It can't see the whole landscape and just walk over to the valley? Nope. All it can do is feel the slope of the ground right under its feet. It has to find the bottom of the entire mountain range using only that tiny piece of information. So, how on earth does it do that? Well, this is the exact problem that calculus was born to solve. It gives the AI the tools it needs for this impossible journey. It acts as the machine's compass, letting it navigate this foggy mountain of error, one careful step at a time, all the way down to the bottom. The most basic tool in the box is the derivative. Think of it like this. If the AI could only adjust one of its millions of knobs, the derivative would tell it the slope in just that one direction. It answers a very simple question. If I nudge this single knob a tiny, tiny bit, does my error go up or does it go down? But of course, an AI has millions of these knobs, not just one. And that's where partial derivatives come in. This is so cool. It's like checking the slope in the north-south direction while keeping yourself perfectly still east-west. And then you check the east-west slope while not moving at all north or south. It lets the AI figure out the effect of changing each individual knob, one by one. And here is where the magic happens. The AI calculates all of those individual partial derivatives, the slope for every single one of its knobs. And then it combines them all into a single vector, one arrow. We call this arrow the gradient. And folks, this is the ultimate compass. Now, the really key insight here, which you can see in some of Eugene Kotoriansky's amazing visualizations, is that the gradient, it points in the direction of the steepest ascent. It tells you the fastest way to go uphill. So what does the AI do? It's not dumb. It just takes a small step in the exact opposite direction. It's that simple and that brilliant. Okay, so we have our compass. It works. Now let's look at how the AI actually uses it to get down the mountain. How does it turn this mathematical idea into actual real learning? The process is called gradient descent, and honestly, it's the bread and butter of how we train almost all of these models. It's this beautiful, simple loop. The AI is at some spot on the mountain. Step 1, calculate the gradient. Step 2, take a little step in the opposite direction, downhill. Step 3, from that new spot, check your altitude. Step 4, repeat. find the new gradient, take another step. It does this over and over and over again until it literally can't find a way to go any further downhill. It's arrived, it's in the valley. Right, but what about these massive deep learning networks with hundreds of layers? If the AI makes a mistake on the final output, how does that correction get all the way back to the very first layer? Well, the answer is another gem from calculus called the chain rule. It basically lets the error signal flow backward through the whole network. It's like a mathematical postal service, delivering a tiny blame report to every single knob, telling it exactly how much it contributed to the final mistake. This whole process, famously, is called backpropagation. And this just shows that there's more than one way to get down the mountain. Gradient descent is like carefully walking, right? Feeling the slope at every single step. But there are other methods, like Newton's method, that use even more advanced calculus to understand the actual curvature of the valley. It's the difference between walking downhill and just sprinting straight to the bottom. Newton's method is way faster, but it takes up a massive amount of memory, which is why for these giant models, gradient descent is still king. So here's the most important takeaway. This is not some abstract theory. This whole process of navigating a foggy mountain of error, it's happening billions and billions of times a second in the technology you're using every single day. I mean, just look at self-driving cars. They are, and I mean this literally, calculus machines on wheels. They are constantly trying to balance all these competing goals: speed, safety, rider comfort, fuel efficiency. The car's computer is just churning through thousands of partial derivatives every second, asking questions like, okay, if I brake just a little bit harder, how much does my safety score go up versus how much does my efficiency score go down? It's just one giant optimization problem, and calculus is the thing solving it. Now, let's just talk about scale for a second. When a large language model, something like Gemma or ChatGPT, is being trained, it's not dealing with 2 or 3 knobs on a radio. It's calculating a gradient for a cost function that has something in the neighborhood of 70 billion parameters. I mean, just try to picture that. You're standing on a mountain that exists in a 70 billion dimensional space. There are 70 billion different directions you could possibly take a step. And yet, calculus, through the gradient, allows a computer to find the one single heading that is the absolute fastest way downhill. It is just mind-bogglingly powerful. So let's just do a quick recap of the journey we've been on. We started with the simplest tool, a basic derivative, just finding the slope for one single weight. Then we leveled up to partial derivatives so we could handle lots of weights all at once. The chain rule let us build these incredibly deep networks through backpropagation. And at the expert level, we even have tools that let us understand the very shape and curvature of the error landscape itself. And that kind of brings us to the final thought. You know, for centuries, calculus has been the compass we use to navigate the landscapes of physics and engineering. And today, it's the compass AI is using to navigate these incredible landscapes of data. So the question is, as our mathematical tools get even sharper, as our compass gets even better, what new, undiscovered valleys will AI find? What problems that we think are impossible today will become just another mountain to walk down? Thanks for exploring this with me.